Okay, so we've already seen a couple Laplace transform pairs, and in this video we're going to go over more Laplace transform pairs. Okay, that is what we're going to do in this video. So let's start with a quick one to start. What about delta of t? What is the Laplace transform of delta of t? And since it's clear we're talking about Laplace transforms, I'm not going to put the curly L anymore. I'm just going to use this double arrow. So Laplace transform of delta t is 1, and we're going to see that the ROC is actually all of the complex plane. So this Laplace transform is going to converge no matter what S value you put into your Laplace transform. So let's see that. So we'll take the Laplace transform of delta of t. This is just delta of t times e to the negative st dt. Okay, so that's the Laplace transform at S. And we know what happens here. We have the integral of delta times some other function. So this integral is going to pick out the value of this function multiplying the delta, where the delta function is located, which is right at t equals 0. So we're going to get e to the negative s times 0, which is just 1. And you can see that this converges. This integral converges no matter what s we pick, right? No matter what that s is, we would have done the same thing and gotten 1. So this converges to 1 for any complex number s. Okay, this means s, that's an element of the complex number, so any complex number s. Okay, so that's why the ROC is all of the complex plane. All right, so that's delta. How about the unit step function? What's this Laplace transform? Well, it's going to be 1 over s, and the ROC is when the real part of s is greater than 0. Okay, and it turns out there's going to be another similar pair, just like we saw with in the previous video, a causal and an anti-causal Laplace transform. And this one, of course, I'll just write it here already, is the causal one. Okay, or right-sided, because the unit step function is a right-sided function, right? It's 0 over here and non-zero to the right. So it's a right-sided function. So this is going to be the causal one of this pair, and we'll see what the anti-causal version is right after this. All right, so let's prove this Laplace transform. So we're going to have the unit step function e to the negative st dt. Okay, that unit step function is 0 when t is negative, so I might as well start the integral at 0. So what do I get? I get negative 1 over s e to the negative st from 0 to infinity. Okay, I'll take that negative and use it to plug in 0 first and then infinity. And we're going to get 1 over s. And then when I plug in 0, of course, I get 1 minus e to the negative s times my infinity, right? This limit as that t goes to infinity. And again, this is why that video on the limit of a complex exponential function as t goes to infinity is so important. We're going to use it all the time. So this goes to 0, provided, okay, what did we see? We needed this thing multiplying our t to be negative, the real part, I mean. We needed the real part of negative s to be negative. That's what we saw. And I can take this and bring it to the other side, and I get, I get a slightly nicer condition that the real part of s is greater than 0. Okay, so provided that this condition holds, this Laplace transform is 1 over s. Okay, so I need that to conclude here to make sure that that goes to 0. Then I'm left with 1 over s. Okay, so let me draw this. Let's draw the region of convergence. Okay, so this is the imaginary part of s. This is the real part of s. And you can see I have a pole at 0. So I'll mark that with my x. That's how people tend to mark poles. Okay, places where the magnitude of the Laplace transform goes to infinity. Okay, so clearly when s is 0, that's the case. And the region of convergence, when the real part of s is greater than 0. So I can draw like a dotted line. I want to be on this side. Okay, so that side is my ROC. Okay, so we just derived this Laplace transform, the long way by hand, but we can also notice actually that this is just a special case of a Laplace transform we already saw, e to the negative at u of t as Laplace transform 1 over s plus a, And the ROC is when the real part of S is greater than the real part of negative A. And we just need A to be 0, right? When A is 0, what do we get? This is just 1. So we get the unit step function has Laplace transform 1 over S. Oops. Can't draw a straight line. There we go. 1 over S, and the ROC is when the real part of S is greater than the real part of negative A. The A is just 0, right? So this is the real part of 0, which is just 0. And that's exactly what we saw, right? 1 over S, and the real part of S is greater than 0. Okay, so you can use sometimes, other Laplace transforms that you have to get new ones. And we'll see more Laplace transform properties in a future video. All right, so if that was the causal version of this Laplace transform 1 over S, what's the anti-causal version? So what's the other function that's left-sided in time that also has Laplace transform 1 over S? And here it is. It is negative u of negative t. Okay, so this has Laplace transform 1 over S as well. But the ROC now is when the real part of S is less than 0. Okay, and this is the anti-causal version of that Laplace transform pair. All right. Okay, so again, we could use this similar special case of the anti-causal version of this function, okay, to prove this Laplace transform pair, but just for practice, let's actually do it out. So we have negative u of negative t, e to the negative st dt. Okay, I'll take the take the negative sign out. And then this unit step function is now going to be 0 whenever t is positive. So I might as well just integrate when t is negative, because otherwise that thing I'm integrating is just 0. Now I'm going to get 1 over s, right? These negatives are going to cancel. E to the negative st from negative infinity to 0. This is just 1 over s, 1 minus e to the, when I plug in negative infinity for t, that negative cancels. Okay, so I'm going to get s times 0, or sorry, s times infinity. And again, this goes to 0, provided, okay, we need the real part of that thing multiplying the infinity, or the t, really, in the limit, to be negative. So we need the real part of s to be negative. All right? That means that term goes to 0, in which case I get just 1 over s for my Laplace transform, and I need that condition to conclude that. Okay, so let's draw this region of convergence as well. Okay, so there's a pole at 0, at s equals 0 right there. And the real part of s being less than 0, that's our ROC, is right there. Okay, so there's our ROC in that case. All right, so now we have the causal and anti-causal version. So again, if someone asked you what's the inverse Laplace transform of 1 over s, you wouldn't be able to answer. There's no way to answer. They have to tell you the ROC, and then you'll know whether you're in the causal or anti-causal case. Okay, next one. So we have cosine of AT u of t. Okay, what is the Laplace transform there? It turns out it's s over s squared plus a squared. Okay, and the ROC is going to be when the real part of s is greater than 0. And we're going to take a to be a real number, right? Because we want to be plugging in real numbers to our cosine function. All right, so let's take this Laplace transform. So we're going to get cosine of AT u of t, e to the negative st dt. Okay, that unit step function means I might as well just integrate from 0 to infinity, because the unit step is 0 and t is negative. And then I'm going to plug in for Euler's formula, or the Euler type formula for cosine of AT to get 1/2 e to the j at plus e to the negative j at, e to the negative st dt. Okay, this is what I get. So then I'll bring the 1/2 outside, and I have this integral, which is e to the what? Well, I have an aj minus s times t for that first term, plus e to the negative aj plus s times t. Okay, so we'll do these integrals. So we get 1/2 times all of this stuff. So it's going to be e to the aj minus st all over aj minus s plus e to the negative aj plus st all over negative, so I'll just put a negative sign there, negative aj plus s. And this is evaluated from 0 to infinity. Everything. All right, so let's plug in. So we're going to get e to the aj minus s times infinity minus what I get when I plug in 0, which is just 1. And same thing over here. I'm going to get e to the negative aj plus s times infinity minus 1 again, what I get when I plug in 0, all over aj plus s. All right, so now we got to figure out, okay, we got to figure out what are the conditions to get this to converge. And you can see there are actually two issues here. We have this term that's causing problems, and we have this term. Okay, so we have two conditions we're going to have to deal with. So let's just look at them one at a time. So what does it take to get this to converge? Okay, so this goes to 0, provided, what do we need? We need the real part of the thing multiplying the infinity to be negative. So we need the real part of aj minus s to be negative, i.e., what's an equivalent condition? I can just split that real part up and get the real part of aj minus the real part of s, bring the real part of s to the other side, and I get the real part of s has to be greater than the real part of aj. Well, what's the real part of aj? Remember, a is a real number, so that's a purely imaginary number. The real part is just 0. Okay? Remember, a is a real number. Okay, so we need the real part of s to be greater than 0 to get this part to converge, but this also has to converge, right? So that goes to 0, provided we need that to be negative. Okay, so we need the real part of negative aj minus s to be negative, okay, i.e., again, just bring the real part of s to the other side. We get the real part of s has to be greater than the real part of negative aj. But again, that's just 0, because a is a real number. Okay, so actually both of these conditions are the same. Maybe they look different to start, but they're actually the same. Okay, we just need the real part of s to be greater than 0. Okay, so we need real part of s to be greater than 0. That's what both of these situations told me. We need that for convergence. Okay, if they were different, then we would need both of them to hold to get convergence, because we need both of these terms to not diverge or have an undefined limit. We need them both to converge. We saw in a previous video that they're going to both have to go to 0. Okay, so now with all of that said, let's suppose that condition holds. Then what do I get? Looking from this negative equal sign, I get 1/2, and I'm going to have, let's see, I can take out that factor of -1, okay, by just switching the order of the terms. So we're going to get 1 over aj plus s minus 1 over aj minus s. Okay, so I just factored out this -1 from both of these terms, which means I just put this negative sign with this function, and this one now becomes positive. Okay, so that's all I did. All right, so now we want to simplify this a little bit, so we can just put everything over a common denominator, and that denominator is going to be this times that. Okay, so I can just kind of multiply this term by aj minus s divided by aj minus s, and this term by aj plus s divided by aj plus s, and combine them. So what do I get? I get aj minus s times 1, okay, minus 1 times aj plus s, all over their product. What do I get for their product? Well, aj times aj is just negative a squared, right? Because j squared is -1. And the cross terms are going to cancel. I get minus aj times s plus aj times s. And I'm left with a minus s squared at the end. Okay, so now I'm going to have 1/2 and aj minus aj, those cancel. And I get negative s minus s. Okay, but then I can factor a negative sign out from the bottom. So I'm just going to get 2s divided by a squared plus s squared. And so that means I get s over s squared plus a squared is how people typically write it. And there you go. So that is our Laplace transform, s over s squared plus a squared. Okay, in the ROC, what condition do we need to get convergence? Well, we have it right here. We need the real part of s to be greater than 0. You can see that's what we wrote. Okay, so that's how you find that Laplace transform. Let's draw what the region of convergence looks like. So the real part of s, imaginary part of s. And where are the poles here? Okay, where does this go to infinity? The magnitude go to infinity? Well, when does the denominator equal 0? What values of s? You can see we need s squared to equal negative a squared. Well, that just means s has to be plus or minus j. So there are poles at plus or minus aj. So that's right up here. Let's say aj maybe is there, then negative aj would be down there. And the real part of s being greater than 0 is my ROC. So I need to be on this side of that vertical line. So this is the ROC. Okay. All right, so that was that Laplace transform. Let's do a similar one. What if we have sine of at u of t? Again, a is going to be a real number. Okay, yeah, write that up there. Okay, then what do we get? Now we get a over s squared plus a squared, and the ROC is going to be still the real part of s is greater than 0. So that's for a sine function. And I'll let you try this one on your own for practice. This is similar proof as above. Okay, pretty much the same thing. You follow all the same steps, just make the necessary changes for sine instead of cosine. Okay, so you can try that for practice. And now we have one more to cover here. So what about e to the negative a absolute value of t? What about that function? Okay. It turns out Laplace transform is negative 2a divided by s squared minus a squared. And the ROC is actually a different type of ROC as we've seen, and we'll talk about this more in a second. It's actually going to be when the negative real part of a is less than the real part of s, and that has to also be less than the real part of a. So it's going to be this kind of little strip in the complex plane, and we also are going to take the real part of a to be positive here. Okay, so that's another condition. Okay, and I'll just make a note here. Okay, note, this is a strange ROC we've seen, and it comes from the fact that e to the negative a absolute value of t is neither causal, or right-sided, nor anti-causal, left-sided. It's neither, but rather it is two-sided. There you can see, what does it look like? It's a exponential function that's decaying in both directions. It looks like that. This is e to the negative a absolute value of t. Okay, so it's not right side, it's not left side. It's not like on one side it's 0 and the other side it's non-zero, right? It's a two-sided function. And so that's kind of, as you'll see, what's leading us to get this ROC that is different than the ones we've seen so far. All right, so let's find this Laplace transform. Okay, so integral from negative infinity to infinity of e to the negative a absolute value of t, e to the negative st dt. Okay, so how do we deal with that absolute value? Well, absolute value is just a function that equals two different things depending on whether t is positive or negative. When t is positive, it just equals t. When t is negative, it equals negative t, right? That's this function. This function is negative t. This function is t. Okay, so when you encounter an absolute value of a variable in an integral, it often is helpful to split that integral up into just when that variable is positive and when it's negative. Okay, so when t is negative on this side, absolute value of t just equals negative t. So I'll plug that in and I get e to the at, right? Plugging in negative t right there, the negatives cancel. I get e to the at, e to the negative st dt. And what about when t is positive? Well, then absolute value of t just equals t. So I plug that in, e to the negative at, e to the negative st dt. Right, so you just consider two cases, but these integrals might look a little familiar to you. Hey, we've seen this integral before. This is just the Laplace transform of e to the negative at u of t, right? Because that u of t, when I integrate it, it'll change my limits like this, okay? And similarly, this is just the Laplace transform of e to the at u of negative t, right? Because now I want the limits to go when t is negative, okay? And how can we make this look like something we've seen before? I'll write this as negative e to the negative at, or sorry, there's going to be a lot of negatives, and I'll explain why I did this in a second, u of negative t. Okay, so why did I do this? Well, I had to try and look at our Laplace transform pair where we had u of negative t multiplying an exponential. And if you remember, that was negative e to the negative constant t times u of negative t. So here I'm taking that constant to be negative a in order to get at there. Okay, so clearly these two functions are the same. I just added a bunch of negatives to make it be in a form of a Laplace transform pair that we have seen. Okay, so since we've already seen these before, okay, we can just use the work we did before. This is the Laplace transform of e to the negative at u of t. Let's go back. I think I wrote it here. Yeah, so we didn't derive it in this video, but I wrote it here when we were talking about something else earlier. So that Laplace transform we can see is 1 over s plus a. Okay, so that Laplace transform is just going to be 1 over s plus a. Of course, you can go through all the work again, but it's exactly what we did before. Okay, and what about this Laplace transform of this function? Well, we saw the Laplace transform of this function was actually the same Laplace transform we got here, right? These were the causal and anti-causal versions. It's just now I have a negative a instead of a. So I'm just going to get 1 over s plus negative a, right? Just to remind you, negative e to the negative at u of negative t has the Laplace transform pair 1 over s plus a. And so you can see all I'm doing is taking that and plugging in negative a for a. And so I get s plus negative a. Okay, that's all I'm doing. But we have this extra negative sign. Okay, so I don't think it's too hard to see if I took the Laplace transform of negative times some function, just bring the negative outside, and then everything is the exact same. You just get the negative of the Laplace transform you got before. So I'll just add in that negative sign right there. Okay. So again, to check this, feel free to go through all of the work, but you'll see as you're doing it, it's exactly what we did to find these other Laplace transforms. So I'm just going to use what we've already done. Okay, but it equaled these things provided the region of convergence conditions were held. What was the condition here? 1 over s plus a. Well, we need real part of s to be greater than real part of negative a. So we need the real part of s to be greater than the real part of negative a. And what was the region of convergence condition here? Well, it was the opposite, right? We needed the real part of s to be less than the real part of negative a. But again, I'm plugging in negative a for that constant. So we have negative a. And we need both of these to hold. And that's important to understand. Okay, we need this condition to hold to make sure this part converges. And we need this condition to hold to make sure this part converges. We need both of them. Okay, so it's the intersection of those two regions is going to be our new region of convergence for this combined function. Let me just simplify this condition on the left. This just means the real part of s has to be less than the real part of a. Okay, so I need both of those things to hold in order to get this expression. And provided they are true, now let's continue with this equal sign. We'll put everything over a common denominator. Okay, so I'm going to multiply this by s minus a, and then I'm going to add it to negative times s plus a and put it all over their product. So I'm going to get negative s plus a, that's this times that, okay, plus s minus a, that's this times that, and it's going to be all over their product, s minus a times s plus a, and so we get s squared, the cross terms cancel, and then minus a squared. Okay, and then finally, just simplifying the numerator, the negative s plus s cancels, so I get negative 2a all over s squared minus a squared. Okay, and that is exactly what we got before, or that we said before. Okay, and now let's talk about the region of convergence. Okay, the ROC, both of these things have to be true. Okay, so the real part of S has to be greater than the real part of negative A, and real part of S has to be less than the real part of A. And sure enough, that is the condition we had before. Okay, just because negative real part of A is equal to real part of negative A. So those are equal. Right, because if I have a complex number that's like x plus jy, and I want the real part of the negation of that, this is just the real part of negative x minus jy. Okay. But that is just going to be negative x. And this, of course, is negative the real part of x plus jy, which is x. Okay, so the real part of the negation of a complex number is just negative the real part of that complex number. Okay. So anyway, so you can prove all these kind of properties with real parts of complex numbers in that way. So real part of negative a equals negative real part of a. Okay, so I'll just leave both of them here so that you're aware, those are equal. All right. That's the region of convergence. So let's draw it. Okay, so what does this look like? It's the real part of S, and this is the imaginary part of S. Okay, remember we said a condition was the real part of A was positive. Okay, so wherever I put my A, I don't know, maybe I'll put it right there. It's my A. I want to make sure the real part of A is positive, which it is. Okay, and now I'm also going to care about negative A, so I'll plot that as well. And if we look, where are the poles in my function? Where does the magnitude of this go to infinity? Well, we can just look where the denominator goes to 0, and that's at plus or minus A, right? When S is plus or minus A, the denominator goes to 0, so the magnitude of the whole thing goes to infinity. So I'll mark these with x's actually, plus or minus a. And now our ROC is when the real part of S is between the real part of negative a and the real part of a. So the real part of a is right there. Real part of negative a is right there. And so my ROC is actually everything in between here. Okay, so this is my ROC. Okay. So previously we've seen ROCs that were like half planes, just to the right or left of a certain dotted line. But now we see one that's actually this sort of infinite strip in the complex plane. Okay, so if I pick any S value in between those two dotted lines in that ROC, then this Laplace transform will converge. Anything outside of it, it won't. All right. So yeah, so that was in this video, we did a bunch of, we found a bunch of Laplace transform pairs and their regions of convergence. And so we're going to be using these pairs in future videos for more examples. Okay, so that's all I have for this video, and I will see you in the next one.